The focus of this lesson is on the important theorems of 3.5, which is complex zeros of polynomial functions. And the first theorem that we're going to come across is the fundamental theorem of algebra, which basically says that if you have a polynomial function that is non-constant, then it is guaranteed to have at least one complex zero. And just to remind you, if you need refer back to the different number types, that I have posted a video on the various number types. But complex numbers are numbers that include every number that you're used to working with: fractions, decimals, radicals, irrational, rational, imaginary, all of those. And so this says there's at least one complex number if you have a polynomial that's non-constant. So then the next theorem is called the factorization theorem for polynomials, and in particular it's talk about factoring over the complex numbers. Later we'll talk about factoring over the real numbers, which is slightly different. But if you take a polynomial of degree n, and we'll say in this case n has to be greater than or equal to 1, then when you go to do its factorization, the leading coefficient that was the leading coefficient prior to it being factored will remain the leading coefficient in its factorization. And so that's our a value that you see listed here. And then if there are n zeros, then there's going to be n linear factors. And if the zero is, let's call it R1, then the factor that relates to it is x minus R1. If the zero is R2, then the factor relating to it is x minus R2, all the way up through all n zeros that you have. So there would be n factors. And these factors may or may not be distinct. It really depends on whether the zero repeated itself or not. And then the next theorem, the number of zeros theorem, it just says any polynomial of degree n has exactly n zeros provided a zero of multiplicity k is counted k times. And so basically what this is saying is the degree is the same as the number of complex zeros if repeats are counted. The next theorem I want to talk about is the conjugate pairs theorem. And basically what it says is if you have a zero of your polynomial that is complex, so it's of the form a plus bi, then you're guaranteed that if that value is a zero, then so is its conjugate. And its conjugate would be a minus bi. And so what that means is the conjugate has the same real part of its conjugate, but it has the opposite imaginary part. So the coefficient of the imaginary part is opposite in sign. And so if one of those is a zero, then so is its conjugate. So in other words, they occur in pair. Non-real zeros occur in pairs. So just an example of that would be if you have 2 plus 3i and you say that is a zero of your function, then you're guaranteed that its conjugate also is. And so the real part is 2, so you keep that, but then you go opposite on the imaginary part, so it's minus 3i. So both of those values would be 0. So if one of them is a 0, then so is the other. You could have something like negative I as a 0, but then that means its conjugate is also a 0. So the opposite imaginary part would be plus I. So that would also be a 0. If negative I is a 0, then it's guaranteed that positive I is a 0. And then we can kind of continue on with this. Let's say you had negative 1 minus square root of 2 I. Then you're guaranteed that negative 1 plus square root of 2i is also a 0. So they occur in pairs. Okay, the next theorem is the odd degree polynomials with coefficients theorem. And it says any polynomial of odd degree with real coefficients must have at least one real zero. And this should follow from the prior theorem if you think about it. So if you're odd degree, that means there's one zero that doesn't pair up. Well, non-real zeros always occur in pairs because you always have the conjugate in itself, right? So the extra guy, if you will, has to be real then, because he's the only way that you have zero that isn't paired up with someone else. And so whenever you're odd degree, just note that you will always have a real zero. The next theorem is kind of an extension of the factorization theorem that we already talked about, but this factorization theorem is where we're factoring over the real numbers instead of the complex numbers. And so in this case, when you see the factorization listed out, you don't want to see those imaginary pieces. And so what ends up happening in this factorization is your leading coefficient of a will still be your leading coefficient of a in the factorization, but some of your factors may be linear and some of them may be what we call an irreducible quadratic. So the linear factors would come from your real zeros, and the irreducible quadratics would come from multiplying together the two linear factors of the conjugate pairs. So you would multiply those factors together. And I have a video showing how to do that multiplication. So at the end of the day, when you're factoring over the real numbers, it may be comprised of your leading coefficient a, and then the real linear factors, and then the irreducible quadratic factors that come from multiplying the conjugate pair linear factors together. So just be aware of all these different theorems and understand what they mean. They do tell you a whole lot of important information. So